and welcome to my Lab 3 report. The purpose of this lab is to predict the behavior of circuits containing resistors in series and in parallel, to use multimeters to measure conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. A preview of my results is that the resistance of the 47 ohm resistor is negative 48 ohms, of the 100 ohm resistor is negative 102 ohms, of both the wire and the ammeter is both 0 ohms, and RC equals 5.988. The model used was the circuit construction kit from Colorado Fed. Fundamental physics principles include the node rule, which states that the current entering a node must equal the current leaving the node, the loop rule, which states that the round-trip potential difference for static electric fields is 0, and delta V equals IR. Part 1. Charge conservation and energy conservation in series circuits. For this circuit on the right, we must predict the currents. Because this is a series circuit, we know that the current is constant throughout. So V net is the sum of the V of the first and second battery, which is 3 volts. R net is the sum of the resistors, which is 47 plus 100, which is 147 volts. And we know I1 equals I2 equals V net over R net, which ends up being 0.0204 amperes. And when simulated in the Colorado FET, both the ammeters do read 0.02 amperes. So if we flip one of the batteries so it's like backwards, the ammeters both read 0 amperes. If we replace one of the ammeters with a voltmeter, the other ammeter reads 0 amperes because the circuit is disrupted by the non-conducting voltmeter. To find the potential differences, we attached each lead of the voltmeter to each of these spots, A to B, B to C, etc. And we know that the sum of the individual potential differences should be 0 volts for a round trip around the circuit, and as my results show, they do in fact add up to 0 volts. This is a graph of the potential versus the circuit. You can see it goes up to 3 volts, stays constant, goes down 0.96, stays constant, goes down 2.04, and then stays constant. Attaching the voltmeter to the circuit does not change the ammeter reading because the voltmeter has high resistance, so it does not conduct electrons, so the current does not change its path. The ammeter reads 0.02 amperes when the voltmeter is connected across the 100 ohm resistor. So when we put one of the ammeters in parallel, the current goes through the ammeter because the ammeter has less resistance, so the 100 ohm resistor is essentially overridden and ignored, making the current higher. So to find the resistance of the components of the circuit, we know that R equals delta V over I. So for the 47 ohm resistor, we get negative 48 ohms. For the 100 ohm resistor, we get negative 102 ohms. And for the wire, we get 0 ohms. And for the ammeter, we get 0 ohms. Part 2, the RC circuit. So connect a 9-volt battery to a 10-ohm bulb and 200 millifarad capacitor. We see that the bulb lights up brightly, then dims until it goes out, as you can see in this succession of pictures. To discharge, disconnect the battery and connect the capacitor directly to the 10-ohm bulb. It lights up and then dims just like it did before. Both when the battery was first connected to the capacitor and 10-ohm bulb, and when the battery was removed from the circuit, the current in the circuit decreased exponentially. The time to charge a 10-ohm bulb was 6.45 seconds. The time to discharge the 10-ohm bulb was 6.19 seconds. The time to charge a 20-ohm bulb was 11.11 seconds, and the time to discharge a 20-ohm bulb was 11.21 seconds. So if I graph time versus the natural log of delta V over delta V naught, we end up with this negatively sloped linear line as we should, and we find that RC equals negative 1 over the slope, which is 5.988. What if an actual ammeter was used instead of an ideal simulated ammeter? The real ammeter would add resistance, making the current read higher. What if a real battery and capacitor with no resistor was used for the circuit? The ideal model predicts the capacitor to reach full charge in about 40 seconds. This prediction would not happen in real life because the battery, wires, and capacitor all have internal resistance. Thanks for watching.